Well, the attendance is very low today. I don't know what's happened. Do you guys know anything? There was anything like, there are no holidays or breaks or anything, right?
Yes, people are probably on assignment on the A2 because it's pretty tough.
I see. Okay, I'll talk with Bojin about it. Okay, anyway, let's start. Any questions before we start? Okay, the main topic for today would be pointer analysis. So I guess I assume everyone are familiar with pointers. We don't have time to cover, basics of C++ or C here. Before we go into that, as you'll know, we had a midterm recently. The results are out. We got an average of around 66%, with the maximum of 97 and the minimum 43. I quickly look through the results so far, and they're pretty much more or less the same like as all the previous years we had. So it turns out the midterm complexity was pretty much in line. You should see your scores, like you can discuss that with Bojan if you need in the tutorial as well. And if you feel like a certain topic is not going well for you, you have enough time to, to fix things until the exam. Traditionally, students do slightly better in the exam than in the midterm, so you should have enough time right now to fix it. Okay, this is the midterm. I guess the maximum 97 was the highest I remember in our midterm. Actually, that was the highest we ever got. Typically, the highest score is around 92, 93, 97 is the highest we ever get. I guess it was not too bad. Yeah, and the average around between 65 and 70 is very consistent over the years. Okay, so what we're going to go today, we're going to talk about pointer analysis, right? There are pros and cons of having pointers to begin with, right? They're an important part of many procedural languages. So as I said, if you learn C++, you're familiar with the syntax, you're familiar with the semantics of the classical pointer, like int star p equals address of x. And this is pretty much both their strengths and their major weakness, right? So that let procedural languages like C being extremely efficient, right? Which is very close to efficiency of assembly language, right? Without sacrificing too. So C can be very frequently being within 20% of efficiency of assembly, while it's much easier to program without a doubt, right? But it also opens up, some issues. So they're convenient, powerful. You can build arbitrary data structures. They're quite flexible. But pointers are quite painful for compiler optimizations. Remember, when two objects point to something, it's very hard to understand in general case what they point to, right? You probably face that if you take someone's unknown C++ code. You look at it, and sometimes it's very tricky to understand what means what and what can overlap with what. And compiler, which is not as powerful as humans, needs to be conservative in their presence. So if you cannot prove two things cannot point to the same thing, they have to assume anything is possible. They can point to the same thing, they can point to the different things, and that limits optimization. So obviously, pointer analysis inspired a lot of research, and this among those problems where people look for a long time. And actually, to the best of my knowledge, I don't believe there is a solution, like an ultimate solution. Like when we schedule and register allocation, there are very decent algorithms available. Pointer analysis brought up a lot of interesting algorithms, but most of them, in a general case, has very high complexity. So that won't really help. Okay, so it's inspired a lot of research. So people try to analyze where pointers are pointing to. There are different options and trade-offs. You're gonna see today something that would be standard precise pointer analysis, where the answer is always like either one or another. You're gonna see things like a probabilistic. So I'm gonna show you some examples of how the pointer analysis might look like. But in general, again, to the best of my knowledge, as a few years, it's still an open problem. scalable, accurate analysis, and I mean scale means with reasonable complexity, still tricky. Like accurate analysis I've seen typically cubic in complexity, right? So, and things are especially difficult when you do interprocedural analysis. So imagine you had a really large program builds up multiple different files, each are all different object files. So in the compiler, when you link them, that's the hardest thing, because now you need to prove pointers between the objects, right? And sometimes between the libraries. It's a very difficult problem to argue with something like that. Okay, so let's start with the basics of the pointer analysis. And if something is not clear, please interrupt me and ask questions. So the first basic definition is the definition of an alias. So two variables are aliases if they reference the same memory location, right? So in practice, what's more useful is to prove not that two things point to the same memory location, but is to prove that two variables reference different locations. So here's an example, and a question to you: what would be the alias sets here? So essentially, this is the code you should look familiar with you and see, right? So just to warm it up, let's look together based on the definition of aliases. So what is point to the same thing? What's point to different things? So we need to define the alias sets here. An alias set is essentially a group of things that point to the same thing. Anyone want to give it a shot? You don't need to define everything, at least some things. You can either mute yourself and talk or chat, both are fine.
So like X and star P, they are alias because like star P is a pointer to the reference of the X.
Mm-hmm.
As well as probably X and star P and star R, they are also aliases because like the star R is just referring to the P.
Mm-hmm. Okay, how about other stuff?
Like Y and star Q, they are also alias, and as well as double star S.
Yeah. So essentially, what we can see is what you said. So we had one alias set, which is X, star P, and star R, right? That's one alias set. Okay. And there's another one, which is Y, star Q, and double star S, right? It's another alias set. And there is another one, which looks like the second one, but it's not, right? Because this is one layer before the reference. So it's Q and star S. Okay. So you pretty much got it right? It's just that that's a little bit of trickiness here. And the important thing is that P and Q point to different locations. You can see they never overlap in any of the alias sets, right? You can actually prove these things never overlap, right? If you do proper pointer analysis. So you got it, right? What the alias is. Because everything else in today's class is going about aliases, right? And we're going to define them with different levels of precision. We're usually going to be less accurate than what you can do when you work manually, right? Right now, you just look manually at the code. There's no control flow, right? There's no multiple functions. So things are more or less straightforward, right? Any questions here? Is it clear, Frank? Since we have such a small class, I can just call you by name and check.
Yes, that's clear.
Okay. So what is the key pointer analysis problem? So we are trying to decide for every pair of pointers at every program point, do they point to the same memory location? Remember, the question asked and how the hour answered it was general for this code fragment, right? And we kind of assume by the end of this fragment. But I mean, as you know, there might be many different locations in the code, and the answer to this question might be different at this different point location, right? Because you might have, call multiple different functions with different parameters. Things could have changed. It's a very difficult problem. It showed to be undecidable, right? So in general case, we cannot solve it. So one problem is we need to be always correct, right? We need to be safe. So we want to repel all pairs of pointers which do may alias. and it can be ambiguous. So essentially 2 pointers which may or may not add. When there is may or may not, this maybe thing usually is treated conservatively. If you cannot prove anything, the maybe means yes, right? So you have to be conservative. You want to be, there's a trade-off here in terms of accuracy precision. So how few pairs of pointers are reported while remaining correct is important. And you try to reduce ambiguity to improve accuracy, because the easiest solution is to claim everything can overlap, right? And you're done. That's going to be a very fast algorithm, but not particularly precise and not particularly helpful, right? Surprisingly, something as trivial as just I said is actually used in practice still to this day in many compilers. Okay, so this is the general problem, right? You already got that, similar to a lot of other problems in this course, it's a complicated problem, right? In general case, undecidable. So we're going to look at some heuristics, obviously. Which optimizations are benefit from pointer analysis? Well, pretty much everything classic: register allocation, common sub-expression elimination, dead code elimination, live variables, instruction scheduling, loop invariant motion. Remember, a lot of these things we looked so far, we avoided pointers for simplicity, right? We were just having regular scalar variables, maybe arrays, but nothing like, not pointer arithmetic. That would add and make all these optimizations actually more complicated. Then parallelization. So people try to parallelize code. There are different forms of parallelism: instruction level parallelism, thread level parallelism. Even if you don't know too much about it, just from the name parallelism, you understand people try to run instructions in parallel or threads in parallel, right? And what limits parallelism is usually the presence of dependencies. So, and what dependencies mean, if, for example, I had a loop, and within that loop is like some pointer arithmetic, I want to parallelize the loop, run pieces of it in different threads. But what's important for me is to prove those two iterations of the loop can be independent. And in many cases, the answer to that depends on whether these pointers overlap or not, depending on the loop iteration. That's what complicated. With arrays, when you use the standard indices, we can use, we can have some linear equations with indices, try to solve them, and we can prove something overlaps or not. But pointers cannot be solved this way, right? So for two loops, if you access certain array with some math for its index, you can just say whether the index can ever match or not, right? You can just solve it. You can see how that can be done. But when it's a pointer P that points to whatever, who knows what, that's a more complicated problem. Then there are other problems like behavioral synthesis. So automatically converted C code into gates. That's a nightmare for people who are dreaming to convert C into Verilog kind of thing. Still having these battles. There are a lot of people in computer engineering working on that. They successfully can generate the code, but the efficiency of this code is very far from the human written code, usually in Verilog. So it's not particularly useful in the applications where I was interested. Then there is error detection and program understanding, memory leaks, while pointer security holes. Every time someone claims yet another big vulnerability, you can 30% chances has something to do with pointers, right? Every time someone discovers a new flaw in one of the operating systems, it's very frequently related to pointers. A lot of algorithms that actually do security or bug detection, they always have special cases for pointers, right? So especially for null pointers. So this thing is important, and the problem is its complexity. There's a huge space and time trade-off here. Comparing every pointer, and can be like thousands and thousands of them, at every program point is complicated, right? And comparing it with every other point, and potentially considering all possible program paths to that point. So you see how quickly that becomes extremely complicated. So you need a trade-off here between scalability, so making any algorithm you do practical, versus accuracy. So different analyses are motivated for different purposes. There were many useful algorithms, generated just to add to the confusion that people try to work in the space. There are always different, special corner cases of something where you have like pointer arithmetic, there's a casting. The really big nightmare is function pointers, because when something passed as a parameter to function, if you don't have properly vision on where it's coming from, you have no clue how their parameters depend on each other, whether they can be the same or different, and whether they can overlap with what you had in the body of the function. Obviously, long jumps is another nightmare because you completely switch the context, right? If you use long jumps. Whole program, this is when I work in the industry quality compilers, was still a problem, and like big compilers like one at IBM, they still struggle with the full interprocedural whole program type of pointer analysis, especially things like library code and things like optimizations at link time were very problematic. Okay, this was more like a selling point motivation on the pointer analysis. And some basic definitions. Now let's look at the presentations. So we define, go ahead.
May I ask a question before we go deeper? So I know like in like a high level languages like C, we have kind of like pointers as a type. But how do pointers represent in assembly language? Isn't that just like a variable with a sort of like a representation by itself?
Yeah, so essentially the way to think about it, always syntactic sugar at the end of the day doesn't exist, right? At the end of the day, the only thing that your machine has is memory, right? So essentially the compiler will have to map all of that to some continuously allocated memory, right? So someone would have to, if you're going to deal with a pointer that points to an individual object, that might be just, a regular variable, like, right? You just had another variable that compute address to where that's stored. So you're going to have loads and stores, right? That's what you're going to see. You're going to see loads and stores instruction, right? That represent that addressing logic, right? So if there is a pointer and you dereference this pointer to access memory, in assembly, there's going to be a special instruction like a load that would compute the address, right? If you like, did you took something like B58 or 258?
Yes, I did.
Class. So remember in that class where we are showing the assembly code, right? We were showing how to deal with arrays, right? And there was like a base. So there was like a base address that you get from the array, right, somewhere. And then you compute the offset. So pointers would be looking very similar like that. That is going to be arithmetic logic. So there's not going to be any magic. There would be addressing logic that would look like addition, subtraction, and there were going to be loads and stores instruction. There are no pointers in assembly, right?
I was just thinking for optimizations like copy propagation, you can just treat pointers like the normal variables, can we?
Well, the problem would be if you can prove, like imagine you want to do copy propagation and for example, you want to see whether it's the same value or not. And in one case, you have A equals B, and in another case, you have A, B being loaded, like instead of B, you have something else that's being loaded from some part of memory. You have no clue what that thing is, right? So imagine there's a function call. Before the function, you push something to the stack, and then you load it from the stack. You know that that would be a variable, but from the little piece of assembly code, it looks like you load something random from the memory, right? Assembly would just say, like, if you're going to write compiler without not knowing the high-level structure of the code, you have to assume that's a random load. You cannot prove anything, right, about it. So probably your copy propagation won't be able to copy propagate through their function call, right? Unless you preserve some information and understand that the stack call, simplify it, and then find what it is. So essentially, copy propagation has to be enhanced for those situations. Like for example, you had a function call. That's a classical example. You had a function called f with parameter a, right? So that a is pushed on the stack and will load it from the stack. So you want to know it's a, but it looks like a pair of store and the load. If you can, in your assembly, you can detect that in between the store and load for the same address, there is no other interleaving stores. you can remove both loads and stores and do copy propagation of this A into the body, right, of the. But you have to do some extra non-trivial optimizations to do it, right? That's where the complication is. So in the higher level code, that information is more visible. But in the assembly, a lot of this information is get lost. That's usually the problem of where the performance is lost. Okay.
I get it. Thank you very much.
Yep. Any other questions? Okay. Okay, let's move on. So I told you about Alias, right? I said you that's an important thing, but I didn't tell you how exactly we're going to represent it. So Alias might have different representations depending on how accurately you want to track it. So if you want to be very accurate, remember in the first examples, we try to make it very accurate. We try track all possible relationships. So one, if you try just precisely all the pointer relationships. So if you had a chain of pairs like that, like star AB, star AE, BE, double star AC, and so on, how that's going to look like is this. We're going to have A separately that just points to itself. Then the star A might point to B, star A might point to E, and B points to E. So you get this triangle. And then for the rest of the equations, for the double references, you had double A can point to C. That's a new thing here. Double A can point to D. But also based on this relationship, if you take this relationship and do star here and star here, you can say that double star A can point to single star E, right? And so on. And then there are all these possible overlaps because if you look here, because, for example, how would I say it? So for example, I know the double star A can point to D, right? And double star A can point also to star E. That means this thing can point to this object as well, right? So as you can see, this is a very accurate representation of the information and what can point to what, but it's getting very complicated and messy very soon. So these type of relationships is usually very tricky to store. So it's the most precise but less efficient. So instead of that, what people track is so-called points to information. So essentially, people just track A can points to B without all the possibilities of how many dereferences there. So you don't see any stars here. So A, B, C, D, all just in objects, right? And the information you track is this can points to this, B can point to C. So the way you store is A points to B, B can transitively points to C, and B can points to D, right? And then E can points to C, and E can point to D. So this is the way you store the information, right? This is less precise because as you can see here, for example, A and E doesn't really, like what would be the good, say A and C, right? Here, say A points to B, B points to C. Here, only two star A can point to C. So if you see star A and C, they actually don't overlap, right? You see this, right? So star A can also overlap only with B and E. Double star A can point to C, right? So in this representation, you'd won't be having the possibilities that, say, star A can point to C, right? So if you're going to see pointer star A and C, you would know those two don't overlap, right, at the same time. But in this representation, A points to B, B points to C, so you might conclude that A can overlap with C. You see, right, the difference in precision, right? Any questions here? So this is a points to relationship. It ignores the notion of a star because that can be very amount of depth and make the representation very complicated because you can have a lot of those smaller graphs all over the place. It's more precise, but it's very hard to deal with. So instead of that, we just interpret like each variable, no matter how many times it's dereferenced, right? And we don't track every individual arrow. Like you see how many extra arrows are here to be more precise. Questions? So this is a more compact, more efficient representation. Okay, any questions? So we are going to use pretty much points to relationships in most of the cases we're going to discuss. Okay, so but I want you to understand this is not perfect, right? It's less precise than a perfect pointer LSE. Okay, so that was the first complication. You can imagine this thing can be very complicated because across each variable and each dimension, you need to have a separate structure like this, right? And track all the transitive relationships. And this points to is much easier, right? If you find two things wherever related in the code, you just have an arrow between them. Okay. Another problem is, as you remember, pointers are not just the ZZ address of B, address of C. Pointers have the heap. I can allocate memory with the functions like malloc, right? And it means I had heap and I need to model it somehow. Or, in the easiest case, I don't model it at all. I just treat that everything is the heap. That's not very precise. So usually what people do, they try to have the allocation site, which is any call to malloc or calloc is treated as an allocation site. And we treat each of these to be a unique location. But we don't differentiate between multiple objects allocated by the same location. So imagine you had a for loop and you had a malloc within that loop. Everything that's coming from that malloc is associated as one thing, right? Because it's just intractable to track every individual allocation, because I might call this malloc 1 billion times, right, in that loop. So we just treat the allocation site as one instance. Obviously, we lose some precision because of that, but that's considered a decent rate. Okay, so this is another options, and another things are shape analysis. So this is like no heap modeling, like the whole heap is treated as one big object. Everything that allocate on the heap can overlap with everything else on the heap. That's very simplistic. Then allocation site, and the more interesting one is shape analysis. So linked list, trees, that. So we know the structure of the object, and then we treat the heap accordingly, right, with the shape. Okay. So what are the other complications are? So when we do it with a point, on all these LSE arrays, right? All these, aggregated structures. How do we model that? Well, for arrays, we can either treat all elements as individual locations, more precise but very complicated if the array is large, or we can treat entire array as a single location, or some hybrid one, treat first or some unique elements as separate locations, because those are usually had separate treatment, but everything else is treated the same way. So those are the way usually arrays are treated. So how about structures? So we had a struct in C or class in C++. We can treat elements as individual locations. That's called field-sensitive analysis, right? Or we can treat the whole structure as a single location. It really boils down to what you want to do or how precise you want your analysis to be. But that's two options. It's either field-sensitive, each field essentially treated as a separate variable, or you can treat it as one single location. Okay, so there is dimensionality with respect to that. So I'm giving you these trade-offs because that's what you're going to see in literature. That's what's going to be important for you in the future. And another thing, another dimension that's important is flow sensitivity. So analysis can be flow insensitive. That means the order of statement doesn't matter. Result of analysis is the same regardless of the statement order, right? I don't look at the if statements you have. I don't look at which order they're running. I just use a single global state to store all the results and they're computing. This analysis is not very accurate, but much simpler because I don't need to have a special representation uniquely for each place of the code. I also don't need to look at different code paths. So flow insensitive is much simpler. A lot of analysis are actually flow insensitive. There are flow sensitive analysis as well. The order of the statements would matter. You need a control flow graph. You need to trick special information across different edges in the control flow. You must store results of each program point. Remember here, there's no, for flow sensitive, you cannot have one answer. Your answer would be different at different place in the code. Okay, and it improves accuracy, of course, but at a very, very non-trivial cost. And then there is plus sensitive, which takes each individual path in the control flow graph in consideration. As very quickly become, exponential in complexity. Okay, so let's do a little bit of an exercise here to practice. So we are still not doing any real algorithm, but we are going to see and trying to make a distinction in different algorithms and what points to what. So first, we'll try to do flow-insensitive analysis here. First, I want to make sure you understand the piece of code here. You had statement 1, A equals malloc, B equals malloc, then statement 3, A equals B. Then another malloc here, then if C, A equals B, and if not C, A equals malloc. And then I dereference A. And I want to know at statement A, what that dereferences can point to. That's a typical questions you ask by the pointer analysis, what that star A might mean at that point. So let's do together flow-insensitive first. So, and then we'll do flow-sensitive and path-sensitive. Let's try to do flow-insensitive first. So the way we represent it is here, there's a malloc. We just called it for simplicity heap S1. Remember I said one representation of the heap is just by the statement, by the line of code, right? So essentially heap S1, it means that malloc that did it, right? It might be in a loop, but in this piece of code, that doesn't matter, right? I just care about that line. So essentially, I allocate memory here, I allocate memory here, I allocate memory here, and also here. For the flow-insensitive analysis, I don't know in which order they execute. I don't look at the if statements. So union of all possibilities is the answer, right? So essentially, I get heap S1, heap S2, heap S4, and heap S6, each of this, right? That's simple, right? That should be clear. Any questions here about flow-insensitive? Just let me know, did you get it or not? Okay, no questions. Try to do flow-sensitive yourself. Remember, there's no algorithm, you're just doing it by just eyeballing it. So what would be the answer in the same notation for flow-sensitive analysis? Flow-sensitive, but it doesn't have to be path-sensitive, just flow-sensitive. Anyone wants to try? It's not that difficult. Come on, just give it a shot.
Could you point to the difference between flow sensitive and path sensitive again? Because I'm kind of like confused with two of them.
So flow sensitive looks at the flow of the executions, but doesn't consider different paths necessarily. You see here, there's if C and if not C. If you're path sensitive, you know you can only take one path, but not the other. Flow sensitive is not smart. It's not looking at the possibility of different paths, but it looks at the order of the execution. So it understands that this is executed and then this is executed, right? And then this is executed.
Okay, so I guess for flow sensitive, you will basically for S1 you will discard it because it's always going to be overridden by the following instructions.
That's correct.
And for all the others, you should keep because you are not path sensitive, so you will assume, right?
Yep, you're absolutely correct. Yeah, that's what I was waiting for. So you see, it's not that easy to discard all others, right? Because of the control flow. So it's in order. So it doesn't know that S5 and S6 are exclusive, right? So it cannot distinguish that. Okay, and now let's look at path sensitive. I'll give you a few seconds to think about it. Anyone wants to try? You can speak it like again, we had a small class today. You can just talk about what you think. So it's a good way to learn.
I think it's heap S2 and the heap S6, because like for the if branch, you're gonna discard heap S4 or anywhere.
Yep. Yeah, you're correct. So if you path sensitive, you would discard. Yep, because it's only one or another. You cannot have that. Okay, good. So you get a feeling of it, right? We didn't pick any algorithm yet. You already see what the requirements can be for the algorithm. There is also such a thing to make it, not to keep your life any easier, there's also context sensitivity. What does that mean? It means you can have different calling contexts, right? There might be different functions. You can be in a different, environment. And that different calling context can have a difference, right? So let me show you one example of that. It's a relatively simple code. You're going to see even for that, it's not an easy task. So we have function main. We had local variable a, b, and the global pointer p. And then there is a statement 1, 2, 3, function call for function f, function call for function g, and p can be assigned address of a here. And this is your function f that assigns p address of b, and my call g function here. And this is the function g. So what is the complication here? So g can call from here, right? But also g can be called from here, right? So you might call f here and f call another g, right? So when you're here, you really don't know how you arrive here, from here or like that, right? That makes the context complicated. So if you're context insensitive, you don't care, right? You just say that this thing can point to either A and B at this point. But if you're context sensitive, if you called, so you can just essentially have, if I'm a function G and you ask me about blah, like star P, then if I'm called from line S5, then the answer is B. If I'm called from S3, then the answer is A. That's the context sensitivity answer, okay? So that depends on the call graph, right? There's such a code thing like a call graph where you track all the function calls. So you get the difference, right? So that's where the difference is coming. Okay, if you don't understand something, please stop. Okay, here, if you ever want to study this thing, I put you a lot of references. This is from the very early papers of Stingard's and Andersen algorithms, that the easiest algorithms. I'm going to actually show them those algorithms to you today. Those are not that difficult, right? We can learn them probably in the next hour, or we'll start in this hour and finish in the next hour. And that's where the pointer analysis started. And that's keep an active area of research to this day. So I updated this slides probably like 3-4 years ago, but there is new papers in the field. Okay, so this is not an area that is like solved really. And you're going to see today why is that, why it's so complicated. Okay, so what is the easiest algorithm we have for pointer analysis, and does it have meaning? There's algorithm exists, it's ultra conservative, surprisingly popular because it's very easy to implement. It's called address taking, right? I want you to know it because it's still used in many production compilers to this date. That's what usually the first implementation of the pointer analysis. If you're not sure what fancy stuff you want to do, you do address taking. It's flow insensitive, context insensitive. It's pretty much insensitive to everything we just learned, right? It's very simple. What it does, it generates the set of all variables whose addresses are assigned to another variable. It just tracks everything that can be an address, right? That was assigned to another variable. And then assume that any pointer can potentially point to any variable in that set. So if something was ever an address, it means it can overlap with something that was an address. If not, then it's not. So for example, if you had, even though it seems like ridiculously conservative, there are a lot of things that never become a pointer or not referenced to anything. Those things would be still properly separated from things that were pointers, right? The main advantage of it is its complexity. It's linear in complexity. You make one pass to the whole program and you have the whole thing, right? Everything is done. It's linear, and linear is your lower bound for that algorithm. You cannot go better than linear, right? So this is why it's still used in many different situations. Okay. Any questions here? Okay. Very imprecise, as you can imagine. Okay. So if you get the algorithms, let's try it out. So let's try apply that algorithms to this piece of code. Remember, we had function main, and we had two other functions, f and g, and this is the way they're called in the code. What I want you to tell me is what the pointer S5 can point to based on the address taken, piece of code. Please give it a try. Please don't just wait. I'm not going to write an answer. I'm going to wait for you to work on it. So that's the whole point. So you practice a little bit. Anyone want to try? Address taken is the easiest one. Okay, so you had heap S1, right? That's one thing, right? That's one thing that should be in your set. Then another thing is heap S4, right? Another thing that's allocated here. Then another thing is heap S6, right? Address taken, right? Malloc. And there's one more, S8. So all allocations. Then what else? Well, everything that has address taken of it. So you had address local, right? In here. So that's in your set. There is address of P taken as a function called here. It means that becomes a parameter, right? So that's in this set. And address Q is in this set. So literally everything here. So it means that if I ask what P can point to here, I'm going to have this long list. Even though you can see these, address local might be very far from it, right? But still, don't know. Questions? So this is your address taken example. Okay, let's start Andersen algorithm. Any questions here? As you can see, it's very conservative. Okay, Andersen algorithm. It's flow-insensitive, it's context-insensitive, but it's more accurate. It's iterative algorithm. Its representation half points to graph of the entire program, where each node represents exactly one location. So essentially, what you do is you use this points to relationship for each type of instruction you may have. So if y has this, if you had expression y equals address of x, it means y points to x, right? This is how you interpret the relationship. If you had y equal x without address, what that means, if x already points to w, then y is now go points to w as well. So y points to what x used to point to. This is how you interpret the assignment. If you had address, if you had star y equals to x, well, that means if y points to z and x point to w, now the z would point to w, right? Because you do the reference here. So it's z that's going to point to w, not y, right? That's the difference. And if you had y equals to star x, so what you do if x points to z, right? And z points to something as well, then y now going to point to that something, which is w. So you dereference x, right? So if it points to z and that points to something else, then y is going to point to something else. That's what that means. So what you do, you take this relationship and apply them like line by line and iterate until the graph no longer changes. So worst case complexity for that algorithm, Andersen algorithm, is order of n cubed, where n is the program size. So this algorithm is going to be more accurate. It's going to be quite complex though. So anyone wants to try this thing? You got right how we deal here. There's this table here. And it's intuitive. That's what you normally do, right? If you were doing it yourself, that's what you usually track, right? You don't track the precise, very precise information, very hard to track, but it's easy to track in your head. Like write a graph saying, if I see this, then I know how to do it. Do you want to try? Anyone want to start build it with me? Okay, let's try it after the break. So I'll give you 10 minutes break now and we'll go back and try it out, okay? So see you in 10 minutes. Is everyone back? Okay, let's continue. Okay, let's try this together and I'll show you the correct results, right? So you've seen me. Remember those rules, right? They're very intuitive, right? Y address X, Y points to X, right? So to any malloc or address taking, right, is what it leads to. And then this is assignment that just goes through, and this is the references, right? So it's indirectly assigned. So. Okay, so what are the main objects here? We had pointer P, right? We had pointer Q here. We had a pointer R here, right? We're going to spend quite some time there because I'm going to use this example for several different algorithms, right? And then we also have a variable local, and we had fp function pointer here as a parameter of function g. Okay. So what we need to do is going line by line. We need to see what kind of relationships we discover as doing that. So the first line is S1. So P equals a log T, right? You can interpret that as a location. We can call it, heap S1, right? So what should I do here in this pointer graph when I see this line?
You create a point-to relationship between P and heap S1.
Yep. So just let me just use an abbreviation here, say heap S1, right? Okay. How about this line? Is anything happens when we call F here? Nothing really, right? We don't pass any parameter here. We'll look into F body later on, right? But first, let's go linearly through the code. So then we had G address of P. What would that do? You see this is FP here.
FP points to address of P.
We can essentially, this points to relationship. We can just say FP points to P.
Oh, I see.
Okay. So, and then we had P alloc T. What would that do?
It's the same thing as S1. Basically, it's S4.
Mm-hmm. Okay, let's look now at the F function. So what kind of information we get here? We have this statement. What would that do?
So Q points to H as 6.
Mm-hmm. That's easy. Oops, I don't know why sometimes it's doing that, but it's okay. Hope we can survive that. I do Control Z. Yeah. It's quite annoying. Okay. Then we had a call for function G with parameter address Q. What would that do? You should know by now.
So just like FP before, so you point to Q.
Thank you. And then you had R equals a log T.
Just like before, you point to H as 8.
Yeah. Okay, and then we had function G, right? Here we had a local variable T, right? If statement and assignment B address local, right?
So P also points to local.
Yep. Did we miss anything? Can P point to anything else? So this is we got our representation, right? Let's stick there for now. We'll see later on whether I'm correct or not. But what the conclusions we can make from that graph. So this is just a sanity check. I think, yeah, we did everything, I think, accurately. I don't see any mistakes, sorry. Yeah, so this is what we got. So based on this representation, I want to say what P can point at S5. So what would be the answer? By looking at that representation.
You just take what P points to in the
so it's very straightforward, right? You see we improved dramatically from address taken. Remember how many different things address taken was pointing to? And local, okay? Is this
so this complexity of n to the q, because that's the worst case, right? But now we're dealing kind of with that.
Yeah, in this case, we were able to eyeball it accurately and do it pretty much linearly, but that's not the worst case. In the worst case, it can be cubic based on how many times you need to go through all the different dependencies, right? Right, remember you need to go through all this relationship multiple times and potentially go backwards, right? Multiple times, depending on the relationship. Because of all this, if that points to that, then you need to look what it points to, right? And all the context that affects you. So Andersen is essentially quite accurate. Its main problem is that it's cubic in complexity, okay? So it means that people could actually use it in some algorithms for smaller size functions, but for large scale code, that might be prohibitively expensive. So this is just shows you the correct answers afterwards. Okay. Can you guys hear me? Okay. Now, people obviously try to improve on that because cubic was too complex. So one option is a so-called Steingert's algorithm. It's also flow-insensitive, context-insensitive. It uses a different, more compact representation of points to graph. So it keeps representation simpler, right? And in that representation, each node can represent multiple locations, but it can only point to one other node. So remember in the previous graph, we have, many different options to what things can point to. But here that we simplify it, we essentially collide some of the information. So there we don't have a node pointing to too many locations, right? We just said you can only point to one other node, and every node has a fan out of 1 or 0, essentially. So it's a union find data structure that eliminates the need to the multiple iterations that leads to the Andersen algorithm being cubic. So worst case complexity here is linear, right? So let me show, and obviously there's a penalty for that. What it's going to do is going to take this representation and collapse some of that information into more compact representation. It avoids the necessity to iterate, so you just you never need to go back and revisit what you have. So everything would be a union, but obviously that information would be less precise. So in this case, right, for the same code, what we're going to have is this thing. So FP, remember this 1, 2, 3, 4, 5, and everything else was showing you how we go line by line through this code, right? And essentially what you see here is how these things, FP edges got collapsed. Remember I had one for P, one for Q, right? And here I made a restriction that my representation can only have one thing. So I merged this, so P and Q got merged right into one node, which also has to merge everything they point to, right? So you get 1, 3, 4, and 7. So this information is merged. And then you had a separate thing that R points to heap S8. So it's not completely wasteful as address taken. As you can see, there is a difference here. It's just it doesn't allows for all this growing set of possibilities, right? That what possible with an Andersen algorithm, because each of them can have multiple different edges, right? So this is less precise representation. The question for you, what would be the answer of Stinger's algorithm for the PS5? It should be very easy by just looking at the representation. Anyone wants to try?
Just heap S1, S4, S6, and local.
Yeah, so it's exactly there. There's no complications here. That representation in compact form keeps your answer. As you can see, this is less precise. So this was the minimal example I can come up that shows you that one algorithm is less precise than the other one, right? So you see here, it has an extra heap that wouldn't be actually possible in real life. So it's worse than Andersen in terms of precision, but it's instead of cubic worst case, it's linear. Again, none is perfect, so you see it loses precision, right? How much, it depends on the situation, but it has a very good complexity. So people obviously want something more like Stinger's in terms of complexity, but at the same time, they want precision more for an Andersen algorithm, because that's already quite precise. So people work on those things. Okay, so let's try to do flow sensitive ourselves. So assume that you can do whatever you want to get the flow sensitive. What would be the answer for PS5 and PS9 if you want to do flow sensitive analysis? Remember the previous two were flow insensitive, both of them. So for PS5, what it can point to if you're flow sensitive?
Just the heap S4, it's like it's right after the alloc.
Yep, yep. How about PS9?
Only local?
And heap S1, I believe, right? Because I overlook one thing, right? Remember, G, I believe, is called two different ways, right? Let me see why I have heap S1 here. So you get, yeah, you might go this way, then go into F, and then F go into G. Let me see, why is that saying that it can be heap S1? I think it cannot be that precise just saying local, because that requires also path sensitivity. So it needs to, yeah, let me look into that myself. I think it should require heap S1 as well, but I'll get back to you on that. I don't remember why I pick heap S1 here as well. I think that's actually the correct answer. So this is function G, and it can be called from here or from here, right? But that's supposed to override no matter what is there. Yeah, I think let's cross this for now. Okay, I'll have a look. Okay. The point I'm trying to make here is you see that information with the flow sensitive analysis is way more precise. even than Andersen algorithm, right? But flow sensitivity is very expensive, right, to support, because you need to look at the order of things, right? Okay, any questions? Oh, I guess it depends. This if statement might play a role, but I'll check later on what I meant by this if here. Okay. Okay, any questions? Okay, so there are a lot of different attempts to improve upon that. I'll just briefly mention some. So one is binary decision diagrams. This is, if you want to study on your own, this is another way to represent the pointer information on different edges and the truth table. And BDD essentially uses the transfer functions where they encode procedure as the function and of its calling context. And it's also both compact and efficient representation. It performs context-sensitive interprocedural analysis, similar to the data flow analysis, but across the procedure call graphs. It gives accurate results and scale up to large programs, so that's something you can use. What I want you to show instead is an example of probabilistic pointer analysis, something that can be speculative. So far, everything was accurate. Everything is either overlaps or it doesn't. And we didn't look at the edges of the control flow graph at all and their probabilities. But there is another way to think about it. The one way to think about pointer analysis is it gives you 3 outcomes, yes, no, and maybe, right? 3 results. And when we look at this intersection, that's, the options. And the maybe is the tricky one because, as we do it, that's where we are not sure. And that's where the most conservatism happens, right? When it's definitely overlaps, we know, and we know how to deal with that. And so is when it's definitely not. So these things definitely not leads to optimizations that we already know to do. The problem with maybe is we have to be conservative in both cases, depending on what the answer we do. And here, usually optimization stops. We don't really do anything for maybes. And the question we ask in these lines of work is there anything we can do for maybe cases where things are not sure? One idea is doing speculation, very common in computer architecture and compilers. So if you want to implement something potentially unsafe, don't just do it. Build a mechanism where you can verify and recover if necessary from your speculation. And try to make sure that speculation is worth it. So for example, if you have something like that, x equal address A, and say A is probably a loop invariant in most cases. What you want to do instead of taking address A all the time here is to move it as loop invariant code motion, right, optimization, into a temporary variable and then access that. So you don't need to dereference the pointer all the time. And then you want to have a code that would verify and recover if you made a mistake here, right? So that's the idea. That's a very high level idea. I'm going to omit all the different, hardware features needed for data speculation. We just look into what that maybe means for us and how we can, benefit from it. So the first thing we want to ask is whether that speculation and aggressive optimization worth it. So we need a way to quantify what the speculations gives me. So remember, by moving an invariant out of the loop, I get some speed up, right? But it doesn't happen all the time now. It happens with a certain probability. So I kind of want to weigh up how much extra overhead I need to do when I'm wrong versus how much benefit I get when I write. So I need some kind of a weighted function to estimate that. So the way to think about it is we want to compute an expected speed up, but not a regular speed up where it's just like one number all the time. This is expected speed up. So we get certain number if we're successful and get some penalty if it's unsuccessful. So to do overhead and verify it. And then there's a probability of success on what we do. And then we make a decision whether it's worth it or not. So essentially the idea here is that so essentially maybe becomes a probability here. So before there was yes, no, and maybe was almost like, you know, no shades of gray in that maybe, right? It was just all maybe, and it means I don't do optimization. Here I get a probability for maybe, and depending on that, I might or might not be willing to do an optimization. So in pointer analysis, remember A and B can point to the same location, and we do this for every pair. We just did it with U. Here we replace this definitely not, and maybe with probability of 1, probability of 0, and probability between 0 and 1. So this is your yes, this is your no, and this is your maybe, right? So this is how we change the classical pointer analysis, where the question is whether A, B can point to the same location. So one advantage of the probabilistic pointer analysis, it doesn't need to be safe. So it doesn't need to be always correct, because proving full correctness might be extremely difficult, right? So the only thing you need to prove instead that you're usually correct, right? Rather than you're always correct. Essentially we come up with a new, I mean, not we, the people who proposed the idea, they actually propose a new accurate points to probability information at every static pointer dereference. And they had a scalable analysis that worked on the old version of the spec benchmark, and they could understand well the scalability and trade-off. So I will go skip over all the details of the design. It's not that important. I will just present what at the end it looked like, so you get a feeling how different the pointer analysis probabilistic can be. So first of all, one difference here that's important to remember, you need profiling. So we didn't do this before, but that's a very practical thing. You do edge profiling. So to get these probabilities, I want some probabilities on the edges of my control flow graph. If I know that this branch is taken 95% of the time and not taken 5% of the time, it's a very useful information I can add at the edges, right? Then you can have safe on safe tag and field sensitivity or field insensitivity. This is all possible features. So let's look at the example of representation here. So the way they present their graph, they had a pointer that's represented as a circle. This thing represents point at, and then the edge can be solid or dotted. Solid line means definitely exist, right, a dependence. And the dotted lines is a maybe. Absence of the lines means definitely not, right? Okay. So if you had a function foo like in here, and you had these, if statements here, right? You had variables A and B, right, as your pointers, right? And then you had X, Y, Z, and undefined as all different variables. And then you build a relationship as you go line by line. So you see here, B points to address of X, that gets right into here. Then A here at the beginning is not it's not known, right? It's a pointer given to function foo. We don't know what it is. We point it to undefined, right? And then as you go here, you get this if statement. So that F statement make assignment B equals address Y. Remember in the previous stage, that was a solid line, right? Now it might have been overwritten with a certain probability here, right? So that makes this line dotted, right? You see, and this new dotted, because this was a solid line, might not be overwrite. Now it's not a solid anymore, it's also dotted, right? And so is when we get here, we had 3 other dotted lines, right? Depending on whether I took this branch or this branch, right? And you see the results are inconclusive. That's what that traditional pointer analysis will do. So here, instead of what we do before, we would add probability to the edges, right? So let's say I did a profiling and find this branch is an average is 10% taken, and this one is 20% taken, right? What I'm gonna do, I'm gonna go to the analysis and I'm gonna get 90-10, right? Spread here on this thing. Then I'm coming here. And then by looking at that branch, right, I have, 20% taken, right? And then depending on, what's that? The other branch, it can be 72% and 0.8%, right? For A, okay? So this is the way it would work based on the profiling, okay? So the idea is the results now provide you with way more information that you used to have, okay? So you actually had the probabilities, right, on each edges. And the idea is that you can actually use this information to make your decisions, knowing how much overhead is for you to recover from misprediction. Okay. Okay, any questions here? Did you get the basic idea? So essentially at the end, for each optimization you want to do, you see how much you save by moving something out and how much you lose because you had a recovery code to fix for the problem, right? Or run it. You know the cost of the overhead, and then you make a decision whether it's worth it or not. Okay. Yep, that's pretty much, I think that's what I want to say here. So they after that, they benchmark, they look at, how work works in practice. One interesting result from that specific work was that the 90% of pointers tend to point to only one thing, right? That's something they learned. So this is why I believe some very simple algorithms are actually possible. So even though the pointers hypothetically can point to anything, in practice, they point just to very few things in the code, right? That's the way we write code, right? We tend not to have these weird global things that point to everything else in your code, right? So most of the pointers are actually simple, and it means they can be amenable to very simple analysis compared to the more sophisticated analysis requires very precise information. Okay, any questions? Okay, well, let's go with the summary. So the summary is we understand that pointers are very difficult to understand at compile time. Accurate analysis are both large and complex. There are many different representations. You need to model heap, aggregate, like arrays, fields, construct representations. You need to be flow sensitive versus flow insensitive. It plays a role. You can be context versus insensitive versus context sensitive. We look at quite a few different algorithms. We didn't look at that one, in the interest of time, but we'll look at address taken, Stingers, and Andersen. Okay, and I'll very briefly show you other options, right? And I spent a little bit more time on the probabilistic analysis, and I took one example, relatively recent paper that can do it. So you get a feeling how that things can get a little bit more complicated, but also more efficient. You see there's different trade-offs here, as usual in this course. Space versus time versus accuracy versus safety. We added a safety dimension here in the probabilistic, example. And essentially, you need to choose the right type of analysis given how much information is available to you and how large is the code to which you run it. So many different programs have different forms of algorithms. They might have Andersen for simple but important pointers. And for everything else that's, say, interactively complex, they might use Andersen, for example, right? Okay, any questions? Okay. Ideally today I had another, 20 minutes to talk about memory optimizations, but we had so few students today. So I don't want to start this topic because that it means everyone else will be behind it. So I'm going to share the slides. You can look at it. It was supposed to talk about caches and everything, but I'll continue that next time because otherwise it would be very wasteful for others. Hope you guys don't mind. Okay, any questions from anyone? Okay. Okay. If there are no questions, that's pretty much it from me. Yeah, if you have questions, as usual, ask them on Piazza. Usually either Bojan or I will jump on them, right? And if you had any questions about your midterm, you can also discuss with Bojan during your tutorial, like if you, some have issues with the grading, and he will discuss with me if needed. Okay. Okay. Then
This is the smallest lecture I've ever attended.
Here's what?
This is the smallest lecture I've ever attended.
Yeah, I've never had that few students either. So I guess a lot of people didn't work on the assignment in the first 3 weeks because they were busy with other stuff. And then it collided with the midterm. We extended already by 1 week, but I guess not everyone finished anyway. So yeah, it kind of affected. Hopefully there will be more people next time.
I used to be in a number theory class, and this was that size, and it was that size every time because by the end we have only that few students left in the class.
Okay, well, that's not the case here. We had quite a few people writing midterm. Like I think it was around 20 people who wrote the midterm,
Yeah.
right? So I don't think the people and the results, the midterm were not that bad. They were like as usual. So don't expect too many people will drop the class or anything like that. Right?
No. Yeah. Of course, this is different. Yeah.
Yeah, I think it's just the assignment, right? So some people are still working. I guess part of the reason also now everything is available online, lecture slides, videos, so you can always, walk and go through that, and you hear all the discussions, all the questions, and then, it makes you less excited to attend the talk because everything is available. Plus, if you don't understand something, there's Piazza to answer your question. So in a sense, it's kind of discourages people a little bit to attend the lecture. I hope it's not going to be always like that. Yeah, anyway. Any other questions from anyone? Fran, Kao? Okay, thanks a lot for attending the class. So see you next week. Bye. Thank you.